So we're going to talk about magnetism. We keep talking about magnets. We need to know how magnets work, why we need the rare earths, and how can we bypass some of the demand of the heavy rare earths. So Brenton did a good job, set up the whole thing application-wise. We already have many things here. Cars is a major one. MRI actually used to have quite a bit of rare earth magnet as a bias magnet. Output MRIs also need the superconducting magnet in the wind turbine. So this one is the direct drive one. The significant difference better located this big plate. That's fair without magnet there. If it is a regular induction one, you will see the thinner box. And even NASA think about put big electric drive at the end of the tail. They would think, why do you need that? Actually, they turn out some aerodynamic reasons. They said if you put big electric turbine at the end of the tail, they can improve the fuel efficiency by 10%. You know what 10% means? The whole margin is about 10%. So this is really big deal. Of course, in MATLAB and hard drive. But actually not hard. I think all the computer nowadays we all use solid state drive, but actually hard drive is still a dominant way of storing data, especially in the cloud, in the data center. So there are 4 categories. If you want to divide exactly how you use your magnet, how do you drive the things. The one we talk about most is the motor here, but there are others using its effect on electrons, for example, the satellite using travel waves to communicate. So we will skip all these things. Now, let's go to the fundamentals. So how do we know a magnetic field exists? We know there are 3 things happen. If there's a force on a current carrying conductor, you will have wires and the current through. If these wires start to move, you'll know something is happening to it, and that something is the magnetic field. The second one is if you happen to have an ion charge, be it positive or negative, and you start to accelerate, you know actually there is a magnetic field. And or there is a dipole. If you have a bar magnet and you start to see a torque on it, there's a force, so there is a magnetic field. So there's only 3 ways to know there is a magnetic field. So how do we generate a magnetic field? Very simple. There's one and only way. It's just the motion of the electric charge. There's no others. So now, how do we find that? Everything started with Hans Christian Ørsted. That's why we named the fields unit after him. It was really 200 years ago. So he said that if you pass a current through a wire, you put a bunch of needles, compass around, it will see strongly start to turn. So that's actually one classic way to determine if you have field present or not. Of course, later Ampere moved in, Faraday moved in, and Maxwell moved in. They all one by one to form the field final. But everything starts with Ørsted. So this is I think this is the second year after Ørsted announced their discovery of this magnetic field. Yad and Salgarat. These are 2 persons actually. So they are working together on something related to violin. I remember Wikipedia told me. They work on that, but then they somehow heard about what Ørsted did on the current carrying conductor continuity field. So they developed this empirical formula to say, okay, if I pass this much of current through a conductor, and then at a certain space, so what it is at this point P, what is the magnetic field going to be like? And they quantify that. So one key takeaway from this formula is, look, this is R squared. So your magnetic field decays as your distance over 1 R squared. So you decay, your magnetic field decay from your current magnet really, really fast. So now this is magnetic field. Now we talk about magnetic induction. So free space, induction and field are pretty much the same, but they are not. There's no such thing as a free space, maybe really in outer space. In air, even air carries certain characteristics of magnetic magnetizations. So not to mention if you happen to pass your field in steel, in ceramic, or even polymer. So So they all have a different response. So you need to add a coefficient in front of the field to describe the induction, what actually you are inducing in your material. And that is called mu naught. And in front of top, you add another coefficient. But in general, if you know the field in the media, and then we know this media exhibits certain magnetic induction, and we call it magnetic flux, and we call it flux density. So in a given space, you have this much of magnetic induction, so that's B. B and H are now the same, although very often treated the same. Unit-wise, you'll hear about Tesla, you'll hear about Gauss, you'll hear about Oster, you'll even hear about ammeter. So what are the relations? So the relation is for the SI unit, the B, the flux density, you're using my term Tesla. And then for the field, you're using ammeter. In the CGS unit, you field flux density, you're using Gauss, and then the unit using Oster. So now let's move on to magnetization. We talk about magnetic material. We define the field, we define the induction. So we see how the field can be expressed in terms of the current. Just remember, Oster 200 years ago showed us we build a wire passing out into the generate field. But in the magnetic material, there is no current. There is no real current. How do we define that? And where does the magnetization come from? So now let's talk about the M. If we talk about big M magnetization, we talk about moment. So how moment happens in the material. So assume we have a bar magnet, and then you generate all this magnetic induction line in the space. So how do we quantify? How do we say your magnet is strong? So how do we measure? So here is the current. So imagine in your each of atom, you have a lot of electrons flying around in a spin around itself, or into the orbital flying around the center nucleus. So there is a current loop, and then ampere is the one who first defined this. They call it ampere bounded loop. You just do a loop using the right-hand rule, and then the current times the area in between. So that's moment. That's one way to define it. Another one is you say, okay, I have a magnetic dipole. There's no such thing called monopole, unmade dipole. Magnetic pole exist in pairs. So one is positive, one is negative. When you say one is north, one is south, they always come in pair. And there is distance separated in between, that's L. So the moment defined as the pole, the strength of the pole, times the length. Two ways to define the moment. You can use in both. One was the others, it's depending on the situation. For the ampere loop, there is no effective length. For the magnetic pole, there is no effective area. You have to give up something in order to calculate moment. So if you have moment occurs and then you now apply your Biot-Savart law, and then you can really calculate exactly where the field where induction is once you know your IA loop, once you know the loop. Or if you don't you want to use in the dipole mode, you can again using the Biot-Savart law to calculate the theoretical point around the field. So now I'm moving step by step toward if we know the source of this current, for example, electron spin in a certain orbit, we can calculate how much field it will generate. So there is this is where 1, 2, 3 is gradually moving to the magnetization of the material. So now, so far, we have two models. One is the ampere loop, one is the dipole model. Both can calculate, give you the field, and both is applicable. It just depends on the situation. You can use in both. Sometimes one is easier, sometimes it's not. But at the end, actually, the result is always the same. Now, move on to magnetization. So if you have a volume, you have this much moment. You divide your moment by the volume. That's your magnetization. So when you apply a field to your material, that's your x-axis, and then you measure the y-axis, your magnetization response of the material. Typically, you start and you're a little bit reluctant, you don't want to do anything, and then you pick it up, accelerate, and then eventually you saturate. There is always a saturation. You cannot keep going the magnetization-wise. So now let's look at the details unit. So let's use an ampere loop. It's always more friendly than the dipole mode. So the magnetic moment is I times A, so current times the area. Therefore, your unit is area ampere times m squared. is current times area for m squared moment. Now you have to talk about the volume effect. You have to talk about magnetization. You divide by volume, therefore you divide it by m cube. So you end up with m per meter. So that's definition. That's the SI unit of the magnetization, m per meter. The energy is magnetization times your moment times your induction. So if we know the energy unit is Earth, and then your field is Austin, and then divide the two, that's the unit of your magnetic moment. That's the CGI unit. So we typically use the EMU. EMU is just an electromagnetic. So don't think they have any other unit. So magnetization in the CGI unit is EMU per cubic centimeter. Versus the SI unit is ammeter. So this is the fundamental things those numbers come from. Now, magnetism so far is always related to electrons. How electrons spin, they may spin around itself, and then the whole electron may do certain orbit around the nuclei. And this is just the one atom sitting in the center of flying around, not to mention there may be many several other second near neighbors that electron can share, can flying around because we call the iterative electron. So one electron, we calculated, this is actually built on quantum mechanics. That electron, the magnetic moment, we calculated roughly because of form magnetron. So this is a H bar, that's a reduced Planck constant, is just the Planck constant divided by 2 pi. ME is the electron mass, E is the charge. This is the unit. So this is the basis. The magnetic moment cannot be smaller than this. Everything is a multiple of this. So now let's talk about physical element. Naturally existing, there are only three elements that are magnetic. One is iron, one is nickel, one is cobalt. Their magnetization wise, nickel iron is really high. This number is wrong. It cannot be nickel is not too high. Sorry, this is wrong. Anyway, so magnetization, there are only three of them. So now we introduce the magnetization into the field. We introduce the induction. So what is the relationship? Actually, there is one. B, the induction to induction is the sum of the field you apply plus the magnetization of the material. So in free space, there is no material, no media. The field and the induction are the same. But the minute you put your iron in, or the nickel, or even some ceramic, or some of the material that is anti-magnetic, to apply a field, you have to generate field the other way. So, and then you have a contact. So the field times magnetization times your constant will give you the magnetization. So in the case for the non-continuous anisotropic material, there may be a undesired distribution of magnetic dipoles on the surface. And those dipoles will generate a field against the applied field. We call it the demagnetization field. This is actually become very important factor. Many applications depending on this, and even the newest gap magnet of iron nitride heavily relied on is HD to make it work. We covered all this basic content. Now let's go a little deeper of the HD demagnetization factor. So I think we just said that if you have a demagnetization factor due to the undesired distribution of the magnetic dipole, and then you generate HD, the overall effective field that you apply to your material is the one you applied, you have minus the one that generated by the magnetic dipole, the demagnetization field. So here's what it looks like. So you see, this is pretty ellipsoid. This is actually mathematically, if you draw an ellipsoid, the charge is more uniformly distributed. And then you can derive an analytical solution of exactly how these fields are distributed. But there are two ways to exaggerate it. One is you can make this ellipsoid really, really long, like a four-way, like a needle. And then that's one situation. Or you make them really, really thin, like a disc, like an oblate, and that's another extreme. So therefore, if you have an analytical solution of ellipsoid, you can naturally extrapolate, okay, what if I'm really, really long? What if I'm really, really short? So here, if you look at let's assume the dipole plus and minus are uniformly distributed on the surface. And then you see there are three fields. One is applied, one is your magnetization, naturally existing. One the demagnetization field, this is red one, caused by the those distribution of surface dipole. And then overall, the green one is the external field. So here, the one takeaway is the further apart of those dipole poles, the smaller the field, the smaller the demagnetization field. So at the end, if you really want to have a total applied field, make sure you counting the demagnetization field. And this demagnetization field is nothing but a geometric factor. So if you have a fixed shape, you can always calculate exactly what is the demagnetization factor and is a function of the magnetization. The stronger the magnetization you are, the worse the shape you are, and then the worse the demagnetization is. There is several extreme case. One is spherical. If you are spherical, and then x, y, z, all direction are all equal. So you are 1/3, 1/3, 1/3. So if you are infinite long rod, so very long, so if you want to magnetize along the long axis direction, parallel axis, your demagnetization factor actually don't have. It's not that. Actually, if you want to do perpendicular to it, actually you are really against something. So here is another extreme example that is really a plate. If you want to magnetize in plane, it's very easy. There's no demagnetization at all against you. But if you want to magnetize perpendicular, well, it's actually very, very difficult. You have huge amount of field to make it happen. So now, imagine if you have a magnetic material, you have a very short one, medium, and excessively long one, and then you want to see the magnetization field, how it behaves. Actually, the shorter one will take more convincing work to do. The long one does not take much. It's very eager to be magnetized. Actually, similar situation happens at even door is when you demagnetize it, what will happens. Curie temperature, we also mentioned that why magnet loses its magnetization at higher temperature. So at lower temperature, all the magnetic domains are aligned, and then once you raise your temperature, all the electron gains kinetic energy. They start to jump around. They start to kind of orbiting more than what they're supposed to, and then you start to lose your magnetization. So there is a particular critical point where actually it's not exactly a point. There is a little range in which before and after this range, you completely lose your magnetic moment. It's not a single point, but for easy to compare, instead of giving a range confusing people, what people do is take a derivative of the magnetization versus temperature, and where they find the first derivative point, so you pick that as your proving point. So here's a list of Curie temperatures. Iron actually is quite good. Cobalt is really nice. Think about 1130. That's red hot, and your material is still magnetic. That's very good. Neodymium iron boron we use a lot. So the active Curie equation under 312 degrees C. So if you really want to use the EH grade or H grade, like 400 degrees C, well, good luck. You are really operating almost half of your Curie point. Actually, this Curie point is not a really good idea to describe as a Celsius degree C. It should be described as Kelvin, because you are really compare your operation temperature in the Kelvin divided by your Curie point and see how far you are from melting point. Here, 312 divided by room temperature to 312 does not really show how close actually you are. Now, another thing is magnetocrystalline isotropy. So this is where we start to touching the concept of coercivity, where the coercivity comes from. So there are many, first of all, we know magnetization is a vector. So depending on directions. It really depending on which direction you measure magnetism, the magnetism may be a good one, maybe a bad one. So there are intrinsic magnetocrystalline isotropy. There's a shape anisotropy, all the nickel magnet depending on the shape anisotropy. And there's magnetic needling. Even you mechanically deform your material, you may introduce certain anisotropy to the material. Of course, there is an exchange anisotropy depending on this one. So now, where is the concept? So let's assume we have iron. Iron is a cubic material. So now assume you have a single crystal, and then you cut a circular disc along this 110 direction. But this is the direction. So this shaded area is 110, right? One bar O actually this direction. Cut one. Now within this disk, you have three directions. You can measure 111, 001, and 111. So you measure the MH curve along these three directions and see how things goes. So here is iron. You'll see it turns out it's very easy. This is single crystal, by the way, right? So it turns out it's very easy to magnetize your material along 110 direction. The second easy one is 110. The worst one is 111. So there is an area in between this 111 and 100. This is a huge whole area represents energy you have to spend to convince your material to be magnetized from this direction to that direction. And cobalt is even worse. You know, for permanent magnet, we really love it because it's a huge area. That means you can store more energy that you can spend later. But if I'm a soft magnet material, I want to convince the material to change transition very quickly. I like this one better. This is easy to do. All right. So now let's dig a little bit deeper at the atomic level. So where does this anisotropy come from? Where does this coercivity come from? So if you think about how electrons spin, it's you see previously I showed this one of this picture. So there's the electron spin itself at halfway, and together you will orbiting around the nuclei. And then you have three other neighbors. Actually, this electron every now and then decide to join to this one. So they call it iterate. So not every one will bond into here. But nonetheless, let's just see how they are bonding, how they are affecting the anisotropy. So there are couplings, this one and that one, or this one along with many other electron happen to spin on the same similar orbital. So that's the spin-spin coupling, all from electrons, spin-spin coupling. Another one is spin with this lattice. Another one is spin with this orbital. So all those things are deciding how willing we can change the spin orientation. And the spin orientation decides our magnetization direction. So first, spin and spin, this one and that one, their coupling is actually very weak. It will not contribute to crystalline anisotropy. It's pretty much just think about it, whatever I'm spinning here has nothing to do with what you are spinning there. They are not really coupled together. And spin to lattice actually has certain degree coupling, but it's relatively weak. So you can think about the lattice consists of quite a few atomic nuclei arranged in space, 1, 2, 3, 4 of them, and each one of them with a cloud of electrons. So this electrons coupling with this overall lattice is relatively weak. And then the orbital, how this electron are spin around, are orbital around this nuclei is strongly coupling with the lattice. Actually, is beyond strongly coupling. I will say this orbital dictate how the lattice are being arranged. It could be cubic, it could be FCD, or it could be hexagonal. It's all because of how your electron are orbiting around the nucleus. So now I move on. So, and then there is one more, is the spin orbital coupling. So the spin, how I spin, and this how I orbital this. This is a tightly coupling together. If I want to change my electron, how I spins, I have to change the orbit. And remember, orbit is strongly coupled with lattice. That means I have to change the lattice. So 1, 2, 3. So there you go. So it's actually at the end, the anisotropy energy is just energy required to overcome this spin to orbital coupling. So right now I'm just painting a picture of one electron, one nuclei, and then you have 4 of them. But if you talk about rare earths, think about 4 F electrons. There are a huge number of electrons available to flying around. How they are arranging relative to each other and how they are affecting neighbors. There's a fundamental reason why we love rare earths. All because 3D electron also play abundant like the iron, cobalt, or even manganese. A lot of them can be helpful, but none of them can do what the white electron. Rare earths and magnetism are tightly coupled together. Now let's move on to permanent magnet. So permanent magnet defined, we also call it a hard magnet. Why we call it hard? Actually, fundamentally, the permanent magnetic property and the hard magnetic property are driven by similar fundamental mechanism. For example, the mechanism we can make a material hard, like dislocation, healing, or defect, all those things. It's the same thing. You can make a magnetic hard. You can make it more strongly magnetic. That's why we often call it, oh, okay, this magnetic is hard. When I say hard, it really means the ability to keep the magnetization longer. So the classic definition of permanent magnet is it can retain its magnetism even after the removal of plant field. Not all magnetic material can do that. Some of the curve, here I draw a red one, but some of the one is just come here and immediately drop to zero. Those things we call it soft. So here you keep going and down. So imagine what I'm going to do, how do I use the magnet is I magnetize it and then I remove my magnetic field. You still have such a magnetization. Now I'm relying on your own magnetization to do work to the external field, to the internal copper bar generated field so that I can generate torque. So here the hard and soft, there is actually rather random, I would say. We say, okay, anything, the coercivity. Coercivity defined as a place where the field required to completely demagnetize your magnet into zero magnetization. So that's called coercivity. So the hard magnet is anything higher than 125 Austed or 10 kiloamp meter. That's called hard. Anything less than 1 kiloamp is called soft. Soft magnet, actually a motor, this is the interesting part. You keep mentioning that you can use induction motor. The difference is induction motor versus permanent magnet motor, you are paying about 10% efficiency. And that 10% efficiency translated into battery cost is actually way more than whatever the magnet pay. Even you pay $250 kilogram of magnet, you're still saving money. But this is why Tesla decided to use the permanent magnet motor about 5-6 years ago. Someone one night they said, okay, my Model 3 can run 10% longer miles from 240 to 300 miles. Very simple to just change the motor from the induction one to the permanent magnet. But induction motor responds much faster. Acceleration is better. But really, the high performance not now is sacrifice a little. This world is always trade-off. There's always again something to do something. So what to make a permanent magnet good? So first, we want the saturation magnetization very high. We want to make random magnetization very high. We want your coercivity very high, so that even as we remove magnetic field, we still can work hard against the external field. So naturally, there are three key parameters for figure of merit to describe permanent magnet. Remnant magnetization, R standing for remanence, C standing for coercivity, BH max standing for the total maximum energy product that you can install into your magnet. I will talk a bit more about how to define this BH max. There were some people making mistakes about that. Here is a real MH curve. This is about manganese business, the magnet that Ames have developed. So you apply the field, pull it up, near saturated and coming back. You leave something behind. And then with the demagnetization field, you quickly lose your magnetization. Eventually become zero. And then you, with the negative field going down, you desaturate on the way. And then this is MH curve. BH curve is different. You have to apply, you have to come to the field you apply. Here's what the BH curve looks like, the orange one. MH curve, you have saturation. BH curve, there's no saturation. Okay, you just keep going. So it's really high. So if you look at here, I said that there is a field required to demagnetize you. So now I see two fields that demagnetize me. One is the MH curve, one is the BH curve. So these two things are two coercivities. So it's two coercivity. Actually, they can be separated quite bit. The one on MH curve is called the intrinsic coercivity, HCI. The one people keep saying, oh, corrosivity, what is corrosivity? Actually, they really mean the HC that means on pH curve, not on the average curve. So you need to make that clear. The energy product is on the pH curve, the maximum area envelope underneath the pH curve. It's a shaded area, the total area. That's where your total energy, maximum energy is located at. When you say 45 megabars of the valve, this means that this one 12, this one 12, and together. So that's the total energy product. So here is one example. Assume you have a straight line of pH curve, and then you pick the maximum one. This is the demagnetization field. In total, you plot the pH curve. You find, oh, here's the maximum number. I happen to be 41.4. So my grade is 40 megabars also set for one magnet N40. So here is the unit. I think in United States or in China, all people tend to use the megabars also, that's unit. But if you go to Japan, you go to Germany, England, they like to use the joule per cubic meter. Either way, it's just a matter of 4 times pi. Either you time it, that's times 12, or divided by 12. So either way. Here is a spec, actually, I'm not sure where it's come. I think you had it actually from Arnold Magnetic, showing the MH curve and the BH curve of the magnet, neodymium iron boron magnet at room temperature, 50 degrees C, 70, 100, 25, all the way to 100. You see how quickly that became. So this is why actually think about if you're using a magnet at a higher temperature, at 200 degrees C versus at room temperature, the corrosivity is completely different. So, and also one thing you'll notice that I'm losing my BR as well as losing my HC. I'm losing them both. This number is called the alpha, how fast I'm losing my magnetization. Because at the end, everybody knows that magnetization is an ordering behavior in volume. The temperature going up, I'm going to become less ordered. So everybody's going to lose your magnetization, no exemption. So this is the alpha, and the horizontally, this is the corrosivity. You are also losing your ordering, actually not ordering, your ability to keep the ordering. So that's the corrosivity. So you're losing that actually faster. This is called beta. Beta is always much worse than alpha. So keep that in mind. So now, let's see, what if I operate my magnet beyond what it should? I just happen to somehow my electronic control went bad. I suddenly send a pulse of a high current. My motor suddenly see 250 degrees C. What I'm going to do? So, or say my magnet is supposed to operate at 125. Now I have to operate at 200. So you are operating this range. So if you are coming down to here, when you remove the external load, variable load, follow this red line come to here. So you are losing half of the magnetization. Then wrong, you're losing half the magnetization. Your motor is going to be damaged unless you take it apart and then put magnet charge it again. Here you're supposed to up on this straight line coming back and forth. This is called the load line. But now you have to go to over this knee. Once you're over that, there's no way return. You have to use your magnet. This is why magnet, the temperature operating magnet is critically important. So now let's talk about grade. You already said out this grade. Typically, I just say N40SH. What this means? This means at room temperature, my grade is 40 megabars Auster, and my magnet is supposed to be operated 150 degrees C. Here is all the SH means 150, UH, EH. H just means high, SH means super high, UH is ultra high, EH extraordinarily high, AH is normally high. So you just keep going this point. So, and look, this is the way we plot this one is very careful. You see, I didn't put the EH, UH, SH directly up and down. Actually, it's slanted toward up. What this means is that EH grade typically you will not be able to do 45. There is no such thing in 45 EH. Go find it. It will not exist. What happened is you have to add in a lot of dysprosium. And dysprosium, terbium, they are non-magnetic. If they are non-magnetic, they dilute your magnetic moment. If they dilute the magnetic moment, they take away your energy product. So the higher temperature you operate, typically the grade of magnet is lower. I think the best one right now you can do, I think in the market, is roughly about N40 SH. And UH is typically you see N38. And then EH, N30. If you can put something here at any cost, even you say I'm selling my magnet is $1,000 a kilogram, if we can do it here, being made, there will be people buy it. So there was a guy running EEC, Electronic Corporate company. He told me, whatever the magnet doesn't, you should just look at the performance and cost. If on the landscape of performance cost, you can find a unique point, there is a market. But you just cannot do whatever other people do. You're just being more expensive. You'll be out of business. Yes.
Ask you first of all, you just said I'm confused now about dysprosium. I mean, they're all inherently, besides gadolinium, not magnetic. It's an antiferromagnetic coupling to iron and dysprosium.
Yeah. Multiple questions of dysprosium added into what?
Well, when you add the dysprosium, isn't it killing the magnetization because it's antiferromagnetic coupling with something?
There is a certain level of antiferromagnetic coupling with your iron, and there is also simple. It's actually not that bad. It is simple dilute of your moment. You add 4%, 8%, even 10%. You're losing that much magnetization, and then the overall energy product is your magnetization squared. So if you lose 10%, efficiently you're losing 20% of your pH rounds.
I'm learning something.
I think you know this story. Anyway, I'm out of time. Am I long?
I'm here.
Am I out of time?
Maybe one more minute.
All right, so I will go this slide. So this is actually an important slide. So this is just you mentioned samarium cobalt, you mentioned neodymium boron. So here is we put them on the same plot. So this is one, the neodymium, we already added the heavy dysprosium. So I perform, this is my MH curve, this is my pH curve. So here is the samarium cobalt. So it's slightly less MH curve, and then here is the pH curve. Now, I put this red line up, this green line up. This means I have a certain magnet with this phase. So if I want to operate that, and then you will see at this point, if I just want to operate 6, at this temperature 6 and 6 kilo outlet, and then 6 Gauss at this range. So this one, you see, the dysprosium one, because it's higher in power density, it takes much less. This is the disk. Actually, this one, it takes much less size and shape than this samarium cobalt one. So higher energy product at higher temperature does kill. You are saving roughly about 25% of water augmentation. So that's the beauty why, despite the dysprosium expensive, this and despite samarium cobalt is always people to go after the dysprosium. It just worth it. Yes, you're expensive, but at the end, at system level, you are still much cheaper. So here is a summary of why or what is ideal for a magnet. We want your corrosivity to be higher than 20 kilo oscillate. We want your magnetization to be 1.4 and higher. We want your energy product to be 50 or higher. We want your temperature to be 135 or higher. I don't want you to react with oxygen or water. I want you to be machinable, ductile, don't break on me. I want you to be cheap, and I want all the material in you easily available. So this is a visual list. This is the current state of art, and here is all the things. I think I want to mention that neodymium boron was developed in the early 1980s. Originally, it was trying to solve the criticality of the samarium cobalt, which happened because of the Republican-Congo's war. But now we are into this stage. This is almost 40 years later. We're still living on the neodymium boron. If we talk about the Morse law, I think there is a new magnet somewhere bound to happen, but it's just way overdue.